Stereocenter in organic chemistry. Stereocenters in organic chemistry. A stereocenter, or stereogenic center, is an atom at which the interchange of two groups produces a stereoisomer. Stereocenters are fundamental to the concept of chirality, which plays a key role in the behavior and function of organic molecules, especially in biological systems, pharmaceuticals, and materials science. The most common stereocenters are carbon atoms bonded to 4 different substituents, forming tetrahedral geometries. However, other atoms like nitrogen, sulfur, and phosphorus can also act as stereocenters under certain conditions. Chirality and stereoisomer. Chirality. A molecule is chiral if it is not superimposable on its mirror image, like left and right hands. The existence of a chiral center, typically a carbon atom with 4 different substituents, often leads to chirality in the molecule. Stereoisomers are compounds that have the same molecular formula and sequence of bonded atoms, constitution, but differ in the 3-dimensional orientation of their atoms. The 2 main types are enantiomers, non-superimposable mirror images; diastereomers, stereoisomers that are not mirror images. Identifying a stereocenter. A stereocenter is typically a sp³ hybridized carbon with 4 different groups attached. To identify one, look for a tetrahedral carbon. Check if all 4 attached groups are different. Example: carbon trihydride CH(O), carbon trihydride right pointing arrow. The central carbon is not a stereocenter. It has 2 carbon trihydride groups. Carbon trihydride CH(O), Cl right pointing arrow. The central carbon is a stereocenter. Carbon trihydride O, Cl, and H are different. Can-Ingold Prelog CIP rules R.S configuration. To assign absolute configuration to a stereocenter, the Can-Ingold Prelog priority rules are used. Assign priorities to the 4 substituents based on atomic number. Higher atomic number equals higher priority. Orient the molecule so that the lowest priority group, usually hydrogen, points away from you. Trace a path from priority 1 right pointing arrow 2 right pointing arrow 3. If the path is clockwise, the configuration is R. rectus. If the path is counterclockwise, it is S. sinister. Properties of compounds with stereocenter. Optical activity. Chiral molecules can rotate plane polarized light. This is measured as optical rotation, with dextrorotatory, D or plus, rotates light to the right. Levorotatory, L or minus, rotates light to the left. Racemic mixture. A racemic mixture contains equal amounts of 2 enantiomers, R and S, which results in no net optical activity. Stereocenters beyond carbon. Though carbon is the most common, other atoms can also serve as stereocenters. Nitrogen, N, in amines, e.g., quaternary ammonium salts. Phosphorus, P, in phosphines or phosphates. Sulfur, S, in sulfoxides and related compounds. However, due to inversion or rapid flipping, not all atoms maintain stable stereocenters unless constrained in a specific structure. Importance of stereocenters in biology and industry. Stereocenters are critically important in drug design. Enantiomers can have drastically different biological effects. Natural products. Most biomolecules, like amino acids and sugars, are chiral. Material science. Polymers and catalysts can have specific stereochemistry influencing their properties. Example: thalidomide, one enantiomer was therapeutic, the other caused severe birth defects. A stereocenter is a point in a molecule where the swapping of 2 groups gives a new stereoisomer. Most commonly, this is a carbon atom with 4 different substituents. The configuration is described using R.S nomenclature based on the CIP priority rules. Stereocenters introduce chirality, which is key to understanding molecular behavior in chemistry and biology. Recognizing and understanding stereocenters is essential for predicting optical activity, biological interactions, and synthetic strategies in organic chemistry.